Good morning, America. Good afternoon, Europe, and good evening, Asia and Pacific. This is the 7th CIRPe Global Web Conference sponsored by the International Academy for Production Engineering. Thanks for staying with us. It is a great honor to welcome you to the opening session of the third and last day of the conference. Like yesterday and on Wednesday, today we are broadcasting this conference live from Berlin, Germany. My name is Pınar Bilge. I'm one of the members of the local organizing committee of the CIRPe Global Web Conference 2019. The series of CIRPe Global Web Conference is hosted by the CIRPe, the International Academy for Production Engineering. Each year, the conference is chaired by a volunteering committee of the CIRPe research affiliates, and it is sponsored by 2 different CIRPe fellows. The content is peer-reviewed by senior CIRPe members and other experts from the field of production engineering. The papers are going to be published in CIRPe at Elsevier, like in many other CIRPe conferences. The conferencing format of the CIRPe conference series is purely digital, which means that there is no physical conference but only online streams like this one on YouTube. You are now attending the 7th CIRPe Global Web Conference, which stands in a row after 6 previous web conferences which are run since 2019. The nature of CIRPe is a cross-domain research. This thought and the discussions we had at our research affiliates meetings, workshops, general assemblies, winter meetings helped us to develop this year's conference theme. The theme revolves around the question how and why production value stream patterns will shift when data, models, and technology is inferred. Let me outline the innovations we introduced this year. First, we introduced 2 highlighted papers on the first day, right after the opening session. These papers highlighted collaborations among research affiliates and gave perspectives of these groups. Do not worry if you have missed it. All of the videos of the first 2 days are available under the link below on YouTube also after the conference. We had a number of 48 scientific papers which were selected and reviewed on a basis of 113 commenters. We are delighted to introduce an industrial panel session just at noontime in Germany today, where we evaluate all of the research papers from an industry perspective. And as last point, we are live on YouTube for all of the 3 days. So coming to the industrial session, this is initiated by Oliver Schwabe from Rolls-Royce, and he's keen with innovation management. He's going to organize and moderate this session on Livestream 1 at noon German time. The main idea of the industry session is giving a feedback to the authors of the 47 contributions from an industrial perspective. And we are going to discuss the results with a panel of multiple experts. Oliver Schwabe is going to moderate the panel, and he's a visiting fellow at Cranfield University and a member of Rolls-Royce Company, compliance partner for IT in civil aerospace. The guests of the panel are Tanja Misfeld, associate partner from the Global R&D and Innovation Services of the Ernst Young Consulting Company, Fiona Sambla, professor for manufacturing technology at the University of Applied Sciences in Berlin, Rene Wenzel, Head of Project Management in Oberursel from the Rolls-Royce company. Chris Campbell, Project Manager at Rolls-Royce PLC. And Andy Nolan, Chief of Estimation Program Management Function from the Rolls-Royce PLC. Thanks to all of you for joining our conference today. So when we go back to the technical side of the conference, all live streams are broadcasted through this YouTube channel. And individual live streams are scheduled for each conference day. You can follow all of these live streams from the links below. Again, the industry panel discussion is going to be on live stream 1, and after our session today, we are going to ask you to switch to the other live stream. Now you are watching live stream 2. Presentations also today are played as pre-recorded videos, and we are relying on your posts on YouTube live chat, where you can write comments and questions to the authors of the papers during the video presentation. We are gonna collect the questions and discuss them in a live questions and answers session with the authors just right after the paper. If you would like to post your contribution or our conference, please use hashtag CIRPe on any social media channel. Let me briefly give you as next an overview about the conference program. This is the last day of the conference. All videos are available under the link below. And on Wednesday, we had the opening session as well as the presentations of 2 highlighted papers. After that, we had 2 parallel sessions on each stream. And stream 1 has started with the session about shop floor operations and maintenance. After that, yesterday, stream 1 continued with a paper session about form-based processes and metrology. After this, around noon, they've started with the session cutting, grinding, and spindles, which we are going to continue in a second on our live stream, and ended up with the value streams and lifecycle engineering session. Today, they are going to continue with the same session on stream 1. We had on our live stream, at the first day, the paper session about automation, planning, and configuration. Yesterday, we had 12 contributions about robotics, automation, and assembly, as well as different aspects of manufacturing, like additive manufacturing, coating manufacturing, hybrid, and incremental manufacturing. Today, we are going to continue with the paper session about grinding. So, today we are going to have 3 papers, and we'll discuss your questions with the authors after each paper. I hope we have earned your privilege of your time so far. Let me start with the first introduction to the first paper of today, which is sent to us from the Institute of Production Engineering and Machine Tools from the Leibniz University, Hanover in Germany. The authors are Mr. Denkana, Mr. Krödel, and Gartzke. The paper is entitled Process Design of the Patterning Process of Profile Grinding Wheels. We are looking forward to your presentation.
Dear ladies and gentlemen, I'm Tobias Gartzke from the Institute for Production Engineering and Machine Tools of the University of Hanover. I'd like to present my research paper with the title Process Design of the Patterning Process of Profile Grinding Wheels. Profile grinding wheels are used in applications such as turbine blades, gear wheels, or crankshafts. Common in these applications is the use of tools that consist of conventional grains. However, these grains face challenges when increasing the productivity of the grinding process. Conventional grains have low thermal conductivity, which leads to a high temperature in the process. This results in tensile residual stresses or grinding burn on the surface of the machined workpiece. One approach to reduce the thermal load on the workpiece is the patterning of the grinding wheel topography. This process is shown as an example on the left. It uses a patterning tool rotating at a higher rotational speed as the grinding wheel. In this example, the tool features only one cutting edge, but a higher number of cutting edges is possible. This approach was investigated for conventional grinding tools in the past. However, it is not yet applicable to profile grinding processes. One reason for this is that the process design, especially with regard to various angles, does not yet exist. To conduct the process design, I choose two steps. First, I calculated the process kinematics in an analytical approach, which is shown here on the left. Within this calculation, simplifications have to be done. In order to validate this approach, the second step, a numerical calculation, was conducted. Therefore, a model was created in the material removal simulation software, IFW CAD-S. The process design uses the established value of the effective contact area. This value can be calculated by the ideal circumferential area reduced by the area of the patterns. As the number of patterns can be adjusted by the process setting parameters, the calculation of the resulting area of one pattern is of interest to the process design. The area can be determined by the length and the width of a pattern. The length can be calculated using a linearized grinding wheel surface. This is compensated by an equivalent patterning tool diameter, which is a common calculation in dressing processes. The width can be calculated by using another simplification. The movement is calculated without a change in angle between the patterning tool and the grinding wheel surface. This is shown on the bottom. The resulting width over length is calculated for two examples, which is shown on this slide. The examples differ in the used shape of the cutting edge. Both shapes are common in patterning of grinding wheels. It can be seen that the triangle-shaped edge leads to a sharp end of the pattern, while the round edge leads to a round end. The shape that results of the round edge can be also described by an ellipsis. In order to transfer this to profile grinding wheels, two angles have to be defined and considered. The angles are shown on this slide on the left. The profile angle describes the angle change of the grinding wheel surface. The inclination angle describes the change from the surface normal direction. The calculation of the length of a pattern, including the angles, can be done calculating first of all an L0. This describes the geometrical interception of the circumferences. When an angle is applied, this circumference has to be projected into the surface normal direction. This distorts the angle to an ellipsis, which is shown in the middle. On the right, you can see that this is similar for the grinding wheel with its profile angle. The length of the pattern can then be calculated by multiplying a factor that prolongs or shortens the L0. The formula for the L0 is shown on the down right. However, the development of this is shown in my paper. The width of the pattern is calculated by the maximum width, which is given at the maximum depth of cut. This width is a result of the shape of the cutting edge. When no angle is applied, it can be calculated by an interception of a circle. When applying an inclination angle, you will get an increase in width whenever the straight part of the cutting edge is tilted into engagement. From this angle on, the width increases with increasing inclination angle. The profile angle, however, has no influence on the width of a pattern, as the patterning tool is defined in surface normal direction. As I described before, I validated this analytical approach by a numerical material removal simulation. On this slide, you can see a result of 3 simulations in which the corner radius was varied. By this simulation, it is possible to evaluate the length, width, and area of a pattern. Obviously, this simulation includes errors as well. The resolution in dexel size and time has an influence on the results. However, the error was calculated and is below 1%. For a validation of the analytical model, the results of the simulation are compared to the results of the analytical model. The analytical model is shown here in green. It is only printed whenever the difference between both models is above 3%. It can be seen that the error increases with the inclination angle. Reason for this is that the shape of a pattern differs. In case of the analytical model, the area was calculated by the ideal shape of an ellipsis. In case of a numerical model, it can be seen that the interacting straight part of the edge leads to a thinner shape towards the end of engagement. This is similar to the resulting shape of the triangle-shaped edge shown before. In addition to the process design, I presented my work first experimental results of the grinding process with pattern grinding wheels. Here you can see the experimental setup. I'd like to highlight the swivel jig that enables the implementation of the inclination angle. Within this study, cast iron was ground using 2 silicon carbide grinding wheels. From the results you can see that the process forces are reduced when applying patterns to the grinding wheel topography. When comparing both grinding wheels, it can be seen that the influence of the patterns increases with the increase in grain size. The reason for this is the interaction between the grains and the surface. However, this is part of the further work of the IFW. This brings me to the end of my presentation, at which I'd like to summarize and give you a brief overview over my further work. As I showed you, the process design is the first step to investigate the influence of patterns on profile grinding processes. I calculated this in an analytical approach, which I validated in a numerical simulation. The further steps are started by the design of the patterning tool. Main part at this step is the investigation on the wear behavior of the used CVD diamond. Then I investigate the contact condition between the grinding wheels and the workpiece surface under the influence of the patterns, followed by an investigation on the application behavior of the pattern grinding wheels. In the end, potential and challenges are investigated that have to be faced when implementing the patterning process to grinding machines. So thank you for listening to my part at this year's CIRPe, and feel free to ask questions or get in touch with me via email. Thank you.
Thank you very much, Tobias, for your presentation and sending us this video. We are gonna getting a call to Tobias right now. That's why you are listening to the Skype call at the moment. We had a delay, so I would like to just ask you to have a 1 second patience. and then I think in a second we are going to be back online. So you're on live stream too on the last day of the CIRPe Global Web Conference, and we are going to have a session with 3 presentations here today. We have been just watching the first presentation from our colleagues from the Institute of Production Engineering and Machine Tools from Leibniz University in Hanover, Germany. The paper is entitled Process Design of the Patterning Process of Profile Grinding Wheels, and the authors are Mr. Denkana, Mr. Krödel, and Mr. Gartzke. So I'm looking at our live chat. There are no questions on the live chat, but we have already received some questions, and I would like to discuss these questions with our presenting author, Tobias Gartzke, in a second. Before doing it, please let me remind you again to get back on Livestream 1 to watch the industry panel discussion at noon German time, as well as closing session. We would also appreciate your posts on any social media about your contributions or our conference with a hashtag of CIRPe. Thank you very much for staying with us. If you have any further comments, recommendations to our conference, it would be an honor to receive them and make the best and out of it and improve the conference series next year with our colleagues from Belgium. Before getting to the Skype connection with Tobias, I would like to also announce you one more time regarding the first live stream. We have a paper session there about the field value streams and lifecycle engineering. I'm looking to my technical support if it works. So far I couldn't get a connection to Tobias. Let me just briefly forward. I think he is calling in at the moment. Could you please check it? Okay. So we have a failure for connecting to Tobias. So let me just send the questions to him through our live chat, and maybe he's able to answer those questions for the commenters. Let me just do it for a second. Okay. You are going to see it in a second on the live chat. So Tobias, thanks again for your contribution, and hope to you can listen to this live chat and can answer the questions. So we have a short break now until the next presentation in order to start with the next presentation on time at 11:20 German time. So please stay with us, and we will be back soon. Thank you. Welcome back. We are online again on Livestream 2 of the 7th CIRPe Global Web Conference 2019. Today is the last day of the conference. We are at the paper session about grinding, and we have been just watching one presentation from our colleagues from the Institute of Production Engineering and Machine Tools, Germany. And the next contribution is from the same institute. So since we had some technical problems connecting to the authors, I would like to combine both question and answer sessions of the first two presentations and continue with both of the presenting authors after the second video presentation. So please feel free to comment and post your questions on the live chat or send them to us. Thank you. So the second presentation of this session is from the Institute of Production Engineering and Machine Tools at the Leibniz University in Hanover, Germany. The authors are Bernd Denkana, Alexander Krödel, and Markus Hein. The paper is entitled Innovative Method for Cutting-Edge Preparation with Flexible Diamond Tools. We are looking forward to your video presentation.
Dear ladies and gentlemen, my name is Markus Hein and I am a research assistant at the Institute for Production Engineering and Machine Tools. I am working in our department for cutting processes and focusing my research on the field of cutting-edge rounding. In the following couple of minutes, I will introduce you to a novel method for cutting-edge preparation for solid carbon tools. For this method, it is essential to know the basic mechanism and influencing factors using the new preparation method. The cutting-edge preparation is a process step in tool manufacture. Cutting-edge preparation is usually carried out after tool grinding and before coating. Irrespective of the considering cutting process, several studies have shown an increase in the performance of cutting tools with a defined cutting-edge shape compared to the ground or sintered initial shape. The increase in performance was attributed to the higher stability of the cutting edge compared to sharp cutting edges. On the left side, you can see the different cutting edge preparations methods currently in use. The most widespread industrial processes are the mechanical processes of abrasive, jet machining, drag finishing, and brushing. On the right, you can see the description of the cutting edge. Symmetrically rounded tools have a form factor of 1 and asymmetrically have a form factor less than or greater than 1. Let me now tell you something about my motivation and my aim. The preparation of complicated tool geometry such as complex end mills poses a particular challenge. An asymmetric rounding offers several advantages. On the one hand, better surface quality and subsurface properties can be achieved by rounding with a shape factor of less than 1 at the surface cutting edge. Furthermore, the tool life can be increased using a cutting edge rounding at the peripheral cutting edge with a form factor greater than 1. However, a reliable production of asymmetrical cutting edge geometries on these complicated cutting tools is not possible today. For this reason, a novel method for preparation of the cutting-edge rounding using flexible bond diamond polishing tools is introduced. On this slide, you can see my experimental setup. All investigations were carried out on a 5-axis CNC milling center of the type ultrasonic 10 by DMG Mori, as you can see on the right. The polishing tools used are provided by the company Ernst Vetter GmbH. They have a diameter of 40 mm and consist of flexible plastic lamellas with embedded diamond grains. The grain size is approximate 20 micrometer. The polishing tools are generally used in a medical technology for processing ceramic dental implants. Uncoated carbide edexel inserts with the SMNR geometry and a wedge angle of 90 were used to analyze the effect of process parameters on the cutting edge rounding and to quantify tool wear. In the initial condition, the insert have a sharp cutting edge with a cutting edge rounding of 5 micrometer. The cutting edge rounding as well as the roughness were carried out with the optical roughness measuring device Alicona and Fight Focus G5 that is based here in our institute in Hanover. During the investigations on parallel polishing, 5 process parameters were partially varied in at least 3 stages in order to identify the influence on the cutting edge rounding. In addition, 2 repetitions were carried out per parameter set. The cutting speed, the feed velocity, the tilt angle, the pitch angle, and the depth of cut were investigated. The target parameters for all processes are the achievable rounding on the flank and on the wake face, described by the cutting edge sections as alpha and as gamma, as well as the form factor kappa. The tilt angle here in the middle top describes the inclination of the polishing tool to flank or wake face during parallel polishing. Using a tilt angle of 0 degree, a flank and wake face are machined equally. At a tilt angle of greater than 0, the machined surface is enlarged on the flank face and reduced on the wake face. The opposite is true for a tilt angle less than 0 degree. However, due to a possible collision between the workpiece and the college chuck of the tool, only a tilt angle greater than 0 could be investigated with the described test setup. The pitch angle defines the inclination of the polishing tool in relation to the horizontal alignment of the tool shank. Due to possible collisions between college chuck and workpiece, only a positive pitch angle could be considered in the investigations. The depth of cut describes the ideal geometric maximum overlap of the workpiece and the polishing tool without elastic effects. Initially, a cutting speed of 440 meter per minute, a feed velocity of 60 mm per minute, a depth of cut of 0.3 mm, a tilt angle of 0 degree and a pitch angle of 0 degree were selected as process parameters. For the initial values, a rounding with S alpha and S gamma 60 to 120 micrometer could be creating during parallel polishing. Due to the direction of rotation of the polishing tool, the lamella pairs first hit the wake face of the indexal insert, polish it and the wake face side, and then hit the flank face, where the polishing time is shorter. This generates more material removal on the wake face, and the cutting edge section as gamma is larger. Thus, an asymmetrical rounding with a form factor of 2 with a high repeatability, as you can see here, can be created. This slide shows the effects of the pulsar settings, feed velocity and depth of cut on the rounding result. On the left side, the influence of the feed velocity on the cutting edge rounding during parallel polishing is shown. Here with a higher feed velocity, the produced rounding and thus both cutting edge sections as alpha and as gamma are reduced on the form factor increases and the form factor increases. The increase in the form factor results from a more pronounced decrease in removal on the flank face and on the wake face. If the feed velocity is reduced, the rounding increases and the form factor decreases slightly. According to the conventional removal hypothesis, material removal during polishing is achieved in the form of an abrasive process in which the usually harder abrasive polishing grain penetrates into the softer workpiece surface and removes material similar to a machining process. Increasing the depth of cut results in a larger rounding, and decreasing the depth of cut results in a smaller cutting edge rounding, shown on the right side. An increase of the depth of cut results in a larger area of the lamella pairs being in contact with the workpiece surface, and as a result more diamond grains can be generated and ablation. The form factor remains almost constant with a slightly decreasing tendency with an increased depth of cut. Yes. For the pitch angle and the tilt angle, similar influences could be identified, as shown on the slide. When the angles are increased, the two cutting edge sections decreases to a certain point. Subsequently, the cutting edge section as alpha rises and as gamma falls slightly. The contact surface between the lamella pairs and the workpiece is first reduced in size on both cutting edge sections. Afterwards, the increase in an angle shifts the contact surface of the lamella pairs to the side of the strength phase, whereby the cutting edge section is alpha rises again. The form factor decreases when the angles are increases and the approaches the value 1. The investigation show that a symmetrical cutting edge rounding can be created with a pitch angle of 45 degree or a tilt angle of 45 degree. Here you can see images of two prepared cutting edges that were taken using a scanning electron microscope to show the quality of the preparation process. The preparation was carried out on the one hand with a brushing process and on the other hand with a diamond polishing tool presented. With both processes, a cutting edge rounding of S alpha as gamma 60 micrometer was created. It becomes clear that the shape of the prepared cutting edge with the polishing tools corresponds to a circle shape. On the other hand, the brushing process with the used process parameters produced a cutting edge shape that resembles a mixture between rounding and chamfer. The resulting edge quality, determined by the roughness value R, is higher with the diamond polishing tools in comparison with the brushing process. In order to determine the productivity of the diamond tool, the tool life of the polishing tools was investigated. The process parameters were kept constant and the wear behavior of the tools was analyzed. In total, the examination covered 50 runs. A light microscope was used to record the conditions of the diamond tools. Dark discolorations are visible on the polisher tips, as you can see on the slide. These become more pronounced during longer periods of use. During polishing, the smallest carbide particles are abrasively removed from the indexable inside and are deposited on the polishing tips in the form of carbide dust. At the beginning of the investigation, fibers and material detachments can also be seen on the polishing tips. If the diamond tools are used for a longer period of time, the polisher tips will also show a wear surface, AV. The surface increases with a further trial. Let me summarize the results. First of all, with parallel polishing, it is possible to produce both asymmetrical and symmetrical cutting edge roundings with a high repeatability. During parallel polishing, all examined process parameters have a strong influence on the cutting edge rounding. In addition, the wear of the polishing tools can be characterized by the surface AV at the polishing tips. The surface increases with further trials. Furthermore, a cutting edge length of 250 mm can be rounded with the same diamond tool without any major change in the preparation result. In the near future, a new tool concept will be investigated. This tool has interlaced lamellas.
Welcome back, and thank you very much for sending us your presentation. So, as announced before, we have online now the authors and presenting author Tobias Gatzke as well as Markus Hein from both presentations this morning. The papers are entitled, from the first presentation, process design of the patterning process of profile grinding wheels, and from the second presentation, innovative method for cutting edge preparation with flexible diamond tools. So we have already posted the questions regarding the first paper on the live chat, and our corresponding author has started to answer it. The other question we received for the second presentation is, which came just in during the last video presentation. I'm just reading this one to you and hope that you can hear us. Or I'm gonna also send it through the chat function to you. So the question is, can you highlight the changing process of the tool by raising up the trial number? We are listening to your answer. So we are.
Yes, it is possible. We can raising up the trial number with further investigation. We need to look up, but I think it's possible.
Thank you for your answer. Could you please also say a few words about your project to fund this contribution? Hello, Markus, can you hear us?
I can hear you.
Good. We have also learned that you have funded the work you just presented through a funding of the Federal Minister of Economic Affairs and Energy. Could you please highlight the importance of the project or of this contribution within the project?
I didn't get the question. Can you repeat, please?
Okay, I'm gonna send the question to you.
Can you repeat the question, please?
Yes. Sure. I'm looking to the left side. Maybe if you mute your sound on YouTube.
It is very important that you have a better process in the future to make work symmetrical roundings for cutting tool. And at the moment there is no possibility to make it work in the industry. So there's a big announcement for the industry to have symmetrical roundings. And so it's nice to have these polishing tools that you can use for produce a symmetrical rounding.
Could you please also detail your challenges for transferring the approach to the industry? Markus, can you hear us?
Yeah, should I answer now?
Yes, please.
Okay, so to transfer it into the industry, there is a problem that we basically now use the polishing tools in other machine. So we need to put our tool into the grinding machine where you produce the cutting tools, and then you have grinding, and after that you can prepare the cutting edge bonding with our polishing tool. And therefore, the next step is to integrate this into the grinding machine, and we will try to work. We'll do it next to the somewhere in the room or in the area where you have the working area. We will put it there inside.
Thank you very much for your explanation. We are going to follow your future work and hope to see you soon. Next question is going to be to Tobias. Could you please also answer the same question for your contribution?
Hello?
Yes, please. We are listening to you.
The same questions that you raised to Marcus, right?
Yes, please.
Yeah. My question was, my project was also funded from the economy ministry, and it's also quite important for the industry that they have possibilities to improve the productivity of conventional grinding tools, and this is a very simple approach. Usually such dressing tools are common in grinding machines, so the technology is quite known and it can be easily applied, but the used parameters are quite different. So all in all, it's a new approach with somehow known tools, so it's easy to apply, and that is why it's funded and also of quite interest to the industry. However, the challenge for transferring it to the industry is that at least one approach or one challenge is that this model, my analytical model, is applied in different scenarios. So each time you can enter some parameters, and this model will give you in a quite easy way as an output how you should pattern the grinding wheel. But the huge challenge is that this in the future should be automated, so that the machine itself knows how to pattern the grinding wheel. And this is one of the huge challenges when transferring it to grinding machines, or in the end to the industry.
Thank you for your...
There are some other challenges, such as the machine room, and the question where you can apply a second dressing spindle and such. But in the end, the major challenge is really the automation of that process.
Thank you a lot for your answers. One remaining question to both of you is, since one of the recent topics of the CIRPe community is the environmental impact of processes and as well as grinding, could you comment on it, how you measure the environmental impact or the change from an environmental perspective through your approaches?
Sorry, I didn't get the last part of the question.
Okay, I'm gonna also type it to you that you can, what is the environmental impact of your approaches?
What is the impact of my process on the grinding
Yes.
process? Yeah. The impact is first of all the topography of the grinding wheel changed. That means that you have a different number of cutting edges and so on in the surface or on the surface of the grinding wheel. That leads to a different load on the grains, but also a different load on the workpiece. You increase, for example, the coolant volume also, and when you have these both effects, you increase coolant and you decrease the number of cutting edges, that leads to a reduced thermal load on the workpiece. And that means that the grinding burn and tensile residual stresses are shifted towards lower thermal loads, or you can use then higher productivity for the same kind of load. And so in this way, this is the main impact. You change number of cutting edges and you change the possible free volume for coolant.
Thanks a lot for your answers, Tobias. Also, thanks a lot for connecting to us through phone, voice call, and looking forward to see you soon. Bye.
Sorry, I didn't hear you.
I'm just saying goodbye.
Yeah, goodbye. Thank you for the conference.
Thank you.
It was good fun.
Thanks also for your feedback. So we are going to continue with our next video presentation entitled Geometric, Physically Based and Numerical Simulation of NC Grinding Processes for the Calculation of Process Forces. This contribution is from our colleagues from the Institute of Virtual Machining at the Technical University Dortmund in Germany. The authors are Mr. Wöst, Mr. Siebrecht, Mr. Fast, and Mrs. Wiederkehr. We are looking forward to your video presentation.
Hello, my name is Florian Wöste and I'm a research assistant at the Technical University of Dortmund. Today I would like to present some recent results about the geometric, physically based and numerical simulation of NC grinding processes for the calculation of process forces by taking the individual grains on grinding tools into account. NC grinding processes can be used for different applications, such as finishing of free-form forming tools. Since the material flow in the forming operation can be influenced by local surface roughness, time-discrete simulations of the grinding process can be used to predict the properties of the resulting surfaces. By modeling the geometric shape of the individual grains on the grinding tools, the surface topographies can be calculated. These are influenced by process effects like tool wear, which has to be taken into account in the simulation. The wear-dependent model of the grinding tools was created by analyzing measured topographies of grinding tools in different states of tool wear. The measurements of the grinding tool topographies were conducted using confocal white light microscopy. Using a binary mask, the individual grains were separated. It was created using watershed segmentation algorithm with a consequent manual refinement. Each of these grains was modeled by a point cloud with approximately 200 points, resulting in a database of representative grain shapes. By distributing instances from this database randomly on the macroscopic surface of the tool, arbitrary tool shapes can be modeled using the same database without conducting further experiments. In order to obtain uniform distributions of the grains on the tool model, Poisson dissampling was used, based on the geodesic distance on the macroscopic surface of the grinding tool. Here, you can see an example of a random distribution of 3,312 diamond grains on a cylindrical grinding tool. Please note that each grain is modeled by a point cloud. Since the grain database contained only about 80 representative grain shapes, each of these point clouds was used multiple times. Based on the described tool model, the initial workpiece surface, and the NC program, the grinding process was simulated by modeling the workpiece as an height field. In time-discrete simulation steps, each individual grain was intersected with this workpiece height field. By subtracting these intersections from the workpiece height field, material removal was modeled. The intersections correspond to the undeformed ship shapes of the grain engagements, which were analyzed to calculate the process forces. The details of this process simulation are described in the following slides. The intersection between the moving point cloud of a grain and the workpiece height field was calculated by describing the sweep volume of the grain in the current simulation step. Since fixed time steps were used in the simulation, the distance between the grain at the beginning of a simulation step and at the end of a simulation step can cause gaps as seen in this example. Therefore, the point cloud of the grain was instanced at additional discrete substeps. The resulting point cloud of the sweep volume was projected onto a sweep height field, which had the same resolution and alignment as a workpiece height field. Due to the inhomogeneous resolution of the point cloud, resembling the sweep volume, morphological filtering operations were used to interpolate between the points. Material removal was simulated by subtracting this sweep height field from the workpiece height field. Here you can see a video of the described simulation system, which can be used to predict the resulting surface topographies based on the individual grain engagements. The grains currently in contact with the workpiece are highlighted. In the detailed view, you can see the point cloud models of the grains as well as a height field of the workpiece surface. In order to calculate the process forces, the undeformed ship shape of each grain engagement was analyzed. Using an empirical process model, the process forces were calculated based on the undeformed ship area. For the purpose of determining the undeformed ship area, the height field segments removed from a grain in a simulation step were projected onto a plane. The normal vector of this plane corresponds to the direction of the cutting velocity of the grain, as you can see in this illustration. The undeformed ship area was calculated as the sum of the differences between the minimum and the maximum vertical coordinates in the coordinate system of the projected plane, which corresponds to the resulting green area shown in the slide. The empirical process force model can be calibrated by determining the correspondence between the undeformed ship area and the process forces using single grain scratch tests. Here you can see the experimental setup based on a rotating workpiece and a fixed diamond grain on its grain holder on a turn milling machine. The workpiece material used was AISI D2 tool steel. A helical scratch with an increasing depth of cut was created, and the forces acting on the grain were measured. The resulting scratches were analyzed to determine the undeformed ship areas and their corresponding process forces. However, the experimental effort is quite high, and the maximum depth of cut is limited by the wear of the diamond grain. Therefore, a numerical process model was used to analyze individual grain engagements. The coupled Eulerian Lagrangian method which is implemented in the commercial finite element software Abacus Explicit, was used as the modeling approach. Thereby, the grain was assumed to be rigid, while the model of the workpiece was described by an Eulerian formulation. Within the fixed Euler domain, the workpiece material was assigned to a predefined field and could move through the mesh due to an interaction with the grain. As you can see in the illustration of the process model, the surrounding region of the grain engagement was discretized by a fine mesh, while distant parts of the Euler domain were meshed more coarsely in order to reduce computing time. The cutting motion was carried out by the grain and is based on the cutting speed used in the experiment. In order to characterize the material behavior during the grain engagement, a coupled thermomechanical analysis was conducted and the constitutive law by Johnson and Cook was applied. In order to describe friction effects during grain engagement, Coulomb's law was used with a coefficient of friction of 0.15. The grain used in the experiments was previously digitalized using confocal white light microscopy, and a mesh was generated as a result. In order to determine the correspondence between the uniform ship area and the process forces, both were analyzed as soon as a stationary engagement was reached. For the selected interval, the mean forces in cutting direction, which is parallel to the y-axis, and in normal direction, which is parallel to the z-axis, were calculated as well as the corresponding uniform ship areas. The cutting force coefficients were then calculated as a ratio of force to uniform ship area. With regard to the experimental results, the uniform ship thickness was varied between 0.5 and 5 micrometers, resulting in a total of 7 different grain engagements. The cutting force coefficients were determined for each process simulation conducted. Here you can see a video of the described numerical process simulation. The material behavior during the grain engagement is highlighted using the occurring Fomesis stresses. The uniform ship thickness in this process was 4 micrometers. The forces acting on the grain amounted to 9.2 Newton in normal direction and 3.8 Newton in cutting direction. The resulting uniform ship area was 236 square micrometers. Based on the results of the numerical simulation, the process force coefficients in cutting and normal direction could be determined by regression analysis as a function of the uniform ship area. A comparison of the experimentally and numerically determined coefficients, depicted on the right side of the slide, shows a sufficiently accurate approximation of the numerical model for uniform ship areas between 38 and 95 square micrometers. Only for very small areas, a significant deviation in normal direction occurs. Generally, the correlation between the force coefficients and the uniform ship area shown in first experiments could be reproduced using the presented numerical model. Therefore, complex single-grain cutting experiments to calibrate the empirical force model can be avoided. To conclude my presentation, I would like to show some validation experiments, which we analyzed using the presented simulation system as well as the process force coefficients predicted by the numerical model. A grinding tool with D427 grains and a diameter of 15 mm was used for this purpose with a cutting velocity of 10 meters per second and a feed velocity of 800 mm per minute. The radial depth of cut was 15 micrometers and the axial depth of cut was 4 millimeters. While significant noise was present in the simulated and measured process forces, due to the high amount of grain engagement, a low-pass filter comparison shows a good correspondence between simulation and experiment, and thus the applicability of the presented approach. Thank you very much for your kind attention.
Thank you for sending us your video presentation. We have been just watching the presentation entitled Geometric Physically Based and Numerical Simulation of NC Grinding Processes for the Calculation of Process Forces from our colleagues from the Technical University Dortmund in Germany. And our presenting and discussion author is now Tobias Siebrecht. Tobias, can you hear us?
Yes, I can hear you.
Great. There are some questions regarding your paper, so I'm going to just read them to you and then would like to ask you to answer those. The first one is, the commenter has written that you have mentioned in your paper the predicted process forces y direction were slightly lower than the measured forces, but a good correspondence was still achieved. What does the difference mean for the process and the results? And what can be done to achieve better results?
Okay, yeah, first of all, thank you very much for having the opportunity to present our research on this conference. And regarding the results, the calculated process forces, there was a slight deviation in the y direction. And we have analyzed the mean value of the process forces and compared the measured values to the simulated results. And in the experiments, we had an average process force of 6.05 newtons in y direction. And in the simulation, it was 5.31 newtons. So that's a deviation of about 13%. And the experimental process forces was slightly higher. But this deviation is not that high when taken into account the assumptions that were made when parameterizing the simulation system. The numerical simulations have been carried out with one representative diamond grain shape, and the rake angle, for example, was neglected. So in future investigations, we could extend these investigations with additional shapes of diamond grains to probably achieve a better correspondence.
Thank you for your answer. I'm going to continue with the second question. This is, what are the potentials of your approach for possible industrial applications?
Okay, so I think there are several potential applications in the industry, and we have to take a look at what can be calculated with our simulation systems. On the one side, we are able to predict the surface topographies resulting from different grinding processes. So one potential application would be the design of a new grinding process or new grinding tools for a specific surface topography which has to be achieved in the grinding process. And the other aspect would be the process forces. And one application could be the calculation of these process forces and the prediction of process vibrations in order to avoid chatter vibrations in grinding processes, for example.
Okay, thanks a lot. And my last question is, since one of the recent questions which we are focusing on within the CIRPe community is the environmental impact of any processes. What do you think for grinding? What is the environmental impact of the research in grinding, and especially your approaches within your projects?
Okay, so I think that one very important aspect regarding the environmental impact is the use of the cutting fluids, for example, in grinding processes. And one possible application of our specific simulation system would be to take the influence of the cutting fluids into account in order to minimize the amount of cutting fluids required in a grinding process, for example. So I think this could be one important contribution to a more sustainable grinding process.
And do you have it on pipeline to work on these aspects?
Yes, it's future research. So we are trying to couple our simulation approach with cutting fluid simulation in order to take this influence into account.
Thanks a lot. We are going to follow your future works and publications. Thanks also for your time, for
Thank you very much.
being here, and hope to see you soon. Bye.
Goodbye.
So thank you all for watching us within the last 3 days. Before closing our session on Livestream 2, I would like first to thank our technical support in the studio, Roger Odari and Cesar Solmas, for their great support. As next, we are going to continue with the industry panel discussion on Livestream 1. So I'm going to announce the industry panel discussion, which is moderated by Oliver Schwabe from Rolls-Royce Company, with experts and fellows from the industry. And they are going to give a perspective to your papers regarding implementation in an industrial field. So if you just click the link below or the QR code, which we are going to show to you after this final words online, you are going to be on Livestream 1, and we are looking forward to see you over there for the last 2 hours of our conference. Thanks again for being with us on the CIRPe Global Web Conference 2019, and I hope we have all the privilege of your time. Goodbye.